Adding random variables. The variance is not simply the sum of the individual variances. Every pairwise covariance enters the formula, counted twice. This single result drives portfolio risk, noise analysis, and error propagation. Setting up the proof. Let Wn equal x1 plus xn. Each xi has mean mu I. The variance of Wn is the expected squared deviation from its mean. Writing the mean as the sum of all mu I, we center each variable to get this expression. Expanding the square. The squared sum expands as a product, the sum over I times the sum over j. Distributing gives a double sum over all pairs I and j. Taking expectation inside, each term becomes the covariance of xi and xj. The variance of Wn equals this double sum of all covariances. The covariance matrix. That double sum is the sum of every entry in the covariance matrix Cx. Row I column j holds COV of xi and xj. Diagonal entries are the individual variances. Variance of the sum equals the sum of all entries of this matrix. The covariance matrix is symmetric. COVXIXJ equals COVXJXI, so every off-diagonal entry appears in a mirror pair. Collect the n-diagonal variances in one sum and count each off-diagonal pair once, multiplied by 2. The formula follows immediately. Special case, independence. When the xi are mutually independent, every off-diagonal covariance is 0. All off-diagonal entries of Cx vanish. The double sum collapses to the diagonal alone. Variance of the sum equals the sum of the variances. The additive rule you already know is this independent special case. The covariance matrix encodes everything. In finance, off-diagonal correlations make portfolio variance explode. In signal processing, they are the cross-correlations you must suppress. Whenever random variables interact, variance compounds.